Okay, today I want to talk about Thevenin and the uses of Thevenin are to completely study components in a circuit. What can happen to a component in a circuit? Well, it's going to work a long time, not have any trouble out of it, right? Sure. What happens, however, if it fails? If I have failure, I'm usually going to get a short or an open. The purpose of Thevenin and Norton, and we'll get to Norton later, is to model a circuit or simplify a circuit based on a component that is prone to fail, in order to find out what's going to happen to it, or how the circuit's going to react, measurements, if you will, in terms of troubleshooting for short and open. It's also a benefit if you've got a component that you want to change. So if I want to possibly change a component and I want to know how it's going to react, what the new voltage drops in the circuit changes will be, this gives me a tool, if you will, to study that. First thing I want to do is pick a component to study. Well, we got to have a circuit. If I go over here and pull up my circuit, that's going to be my result. Here is my circuit. As you can see, I've got a 10-volt source with a 1K resistor, a 2K resistor, a 3K resistor, whoops, there's the 3K, and the 4K resistor. When you're doing Thevenin analysis, you can study any resistor in the circuit. However, voltage sources, by definition in the real world, have series resistance, or they have internal resistance with them. So for the purposes of Thevenin, I'm never going to ask you to study the resistance that is in series with a voltage source, particularly if there's only one voltage source in the circuit. If there's two, then it's possible. If there's only one, then basically the method fails. If this had internal resistance and you knew what it was, then yes, you could study R1, but for practical and easiness of this exercise, you can study R2, 3, and 4 all day, but we're going to stay away from anything that's in series with my voltage source, just to make it easy. So let's pick R2. So there we go. I've got R2 picked. I have just decided I want to see what happens with when R2 is gone. So pick a component to study. I picked R2. Okay. Now what? Now I want to remove R2. Or remove the component, I should say. I want to keep this pretty generic. Remove the component. Find and maybe measure or calculate the voltage drop across the open. This will become my Thevenin voltage. And I'll type it all the way out just to make sure. This will become my Thevenin voltage. Alright, so I'm going to pick a component. I'm going to remove a component. The way I do that is I go up here and I think I hit delete. Gone. Now, I've got the component open. If this was a circuit in a lab, I could simply turn things on, put a voltmeter across this opening, measure my voltage, my DC voltage in this case, and that would be my Thevenin voltage. As part of an electrical electronics program, students should be able to analyze this circuit. What is my voltage drop? One thing to keep in mind, if I take this component out and I've got an open circuit, I have lost my current path. And so when you're dealing with Thevenin circuits, the most difficult thing that students struggle with probably is the fact that they lose their current path. And if they lose their current path, that means there's no current flowing over here where I've got the cursor moving. If I have no current flowing through R4, then I have no voltage drop across R4. So this point, from a voltage standpoint, becomes identical to this point. This point becomes identical to this point. And I want to reinforce that a little bit. If you remember Ohm's law, V equals IR. If I equals 0, then V equals 0, regardless of what R is. So I want to reinforce that a little bit, and it's a good review, and it's a good way to think about it in terms of what's going on in here. So what I really need to do to find the voltage drop across here in terms of calculation is it will be identical to the voltage drop across my R3 resistor, which incidentally still has current flowing in it because I have a complete path from one side of my battery to the other. And anytime I have a complete path, then I will have current flow. So I've got 10 volts with a 1K resistor and a 3K resistor. So I'm going to take my 10, divide it by my series resistance of 4K. It's going to give me 2.5 milliamps. 2.5 milliamps times 3K is going to give me a voltage drop across this 3K resistor of 7.5 volts, which is what I would measure here if I built the circuit. Feel free to build the circuit. The more you build the circuit, you get used to doing things in the lab, you get used to the calculations, you see how it all fits together, the greater your confidence becomes. So let's go back to here. Doing the calculation, I got 10 volts divided by 4K, or 4,000, will equal 2.5 milliamps. And then I'm going to take my 2.5 milliamps times my 3K, and that will equal 7.5 volts. Alrighty. That voltage is my Thevenin voltage. So my V Thevenin is equal to 7.5 volts. Alrighty. We got that there. Alright. What's the next step? 3. My next step is to figure the resistance back through the circuit. Alright, Jim, what are you talking about? Well, let's look at the circuit for a minute and I'll tell you what I'm talking about. If I start at this point and I go back through the circuit, see, I have to go through resistors to get to this point. And in this particular circuit, I have multiple paths, so I can go through this resistor and through this voltage source and around through this resistor and get back to there as well. So essentially, I leave here, I come to this split, and I can go two ways. I go either way, I come back to this split, come together, and then I have to go through a 4K. In Thevenin, we have a special rule. Voltage sources I treat as short circuits for the purposes of this step. If you were in a lab and you were wanting to measure your Thevenin resistance with an ohm meter, you would have to remove your voltage source and replace it with a wire. That's what I'm talking about. So figure the resistance back through the circuit. Voltage sources I treat as a short. I treat as short circuits. Treat as short circuit. Okay. Later on, we're going to talk about Norton, and so I need to add this part. Current sources, I will treat as an opened. Now, where this typically is taught in the classes that I teach, we haven't really talked a lot about a current source. Voltage sources is something that will give you a constant voltage and will source however much current it needs to in order to maintain that voltage drop through your circuit. A current source is sort of the reverse of that. It's going to source a certain amount of current, and it will change its voltage in such a way that it will source whatever current value it's set at. So everybody's a lot more familiar with voltage sources than current sources. There is a real world equivalent of a current source, and that of course is a transistor, and that's sort of where this course is heading, into transistors. So we will get into current sources. For the purposes of Thevenin, voltage sources I treat as a short circuit, current sources I treat as an opened. That's the process. If I go to back to my drawing and I remove this, which I'm not going to do, put a wire through it, I will ask you to visualize that. Then what you see is I've got a 1K in parallel with a 3K resistor, and then a series resistor beyond that. So I've got two here in parallel and one here in series. If I want to solve that, then I'm going to pull up my calculator that I use, and I'm going to figure out that. So I'm just going to use the parallel resistance formula. 1 divided by 1000, or 1K, plus 1 divided by 3000, or 3K, and then I'm going to add that to my 4K resistor, or my 4000 ohm resistor. So I get a resistance back through the circuit equal to 4750. Okay? So the circuit I picked, based on the resistor I picked, analyzed my circuit. I analyzed the circuit back through, and in this case, for my example, I get 4750 ohms. That's it. Once you have your Thevenin voltage and your Thevenin resistance, and this is what we just did, R Thevenin equals 4.75K. Once you have your Thevenin voltage and your Thevenin resistance, now you can get your Thevenin circuit. Alrighty, I went ahead and drew one. A Thevenin circuit is that voltage source and that resistor in series. So if I put in my voltage source here, 7.5, enter, and my resistance here, 4750, whoops, enter. Now that is my equivalent Thevenin circuit for that. So I can change this. I can put a short circuit here and figure out the current that would flow through it. And I could go through circuit analysis and figure out the current when my 2K resistor shorts. Or I can come over here to my Thevenin circuit and put a wire between these two, and as you can see, it would be much easier to calculate the current. They would be the same. Going back to my Thevenin circuit, what happens if it opens? I'll read a voltage drop across here, and who knows what it'll be. We already knew because we did it as part of the process. If I put my voltmeter across here, Again, no current flow, no voltage drop, so the 7.5 would be what I would measure. Alright, that sort of gives you the open, infinite resistance, and zero resistance. If I put a 2K resistor in there, then with this circuit I would know the voltage drop across 2K resistor. I could calculate the current through the 2K resistor. I can do that over here on this circuit just with standard circuit analysis. The value of Thevenin comes in what happens if instead of a 2K I want to put a 1K in. If I put a 1K in here, then I've got to go back and do all my circuit analysis for my voltage drop, my current through it, or since I have since I have come up with a Thevenin equivalent circuit, all I have to do is put a 1K in here. I can then calculate the voltage drop. I can come up with the current through. Much easier, and that's why we do it. Now, in terms of practice, what you can do is put the 2K resistor back, and I don't want it to say R5. I want it to say R2. I want it to say 2K. But what if I wanted this to be a 1K? Or a 10K? Or a 100K? Now I can do it. I've got the circuit for that one. What you can do is, okay, go through the process, come up with the Thevenin equivalent circuit for R3, or come up with the Thevenin equivalent circuit for R4. There we go. You can do either of those. The steps are as you see here. And I make the type big so you can see it. I should be able to scroll up. You've got 3 steps. You're going to pick a component. Obviously, you'd pick a different one. You'd remove the component, use your standard steps to figure out exactly what your voltage drop would be, Thevenin voltage. There's my example. Your example would be different if you pick a different resistor. Then you can figure the resistance back through the circuit. You'll get different answer if you pick a different resistor. The process, however, is the same, and that's what we're after. Process. I hope this helps you, and I hope you can watch this and see, and I suggest you do pick a different resistor and you do the calculation so you can come up with different values.